These are my two friends, Erica Davis and Jemiah Sanders. And as a group, we collectively research about falling objects and the effects that gravity has on acceleration and how they both land at the same time, how objects can land at the same time. First of all, I would like to go into detail about how exactly we came about this experiment and where this experiment derived from. In 1589, a scientist and theorist by the name of Galileo performed two different experiments using objects of different masses. Initially, he thought that Aristotle, who was another philosopher / scientist, original theory that two different objects of two different sizes and masses would drop at two different rates of acceleration. Now, initially, you may think that, okay, this is a good theory because if something is light, let's say a feather, opposed to something that's heavy, let's say a bowling ball, it only, in your mind makes sense that the feather drops slower because, it would float down, right? So, initially Galileo was like, okay, Aristotle might be right. So he put this to the test by dropping two different masses from the Leaning Tower of Pisa and found out that there was something a little bit strange about this initial theory. He found that, initially the two objects looked as if they were dropping at different acceleration rates, but he put the feather in the bowling ball or feather in this other object that was heavier than the feather into a capsule to alleviate what Mr. Jones was talking about before, which was air pressure. He found that air pressure had a lot to do with the look of two objects falling at different acceleration rates. Exactly. So he put the two objects into a vacuum, which, like I said, alleviated air pressure. After that, he realized that, wait a minute, two objects of different masses, different sizes, actually fall at the exact same acceleration rate. And I thought this was interesting, particularly looking at the math part. I'm going to walk over here to write exactly why. But there are three different systems that are used worldwide to convert measurements. And right now I'm going to be writing down, not necessarily an equation, but those three systems. First you have your CGS system. And CGS stands for centimeter grams per second. That is 980 over centimeters. Can you read that? I might have read it.
Perhaps you can try to use a big chalk. Use a big piece of chalk.
That's a great idea. You probably can rub off the names now. Use the blue chalk.
The next one is 9.8 meters. Over seconds squared. This one is called the MKS system, and both of these together are the metric system. Now, we also have the English system, which is 32 feet per second squared. Now, I found it kind of ironic how all three of the denominators were the same. It was second squared. So, out of curiosity, I wanted to find out exactly why that was. Now, if you look at the idea of acceleration, acceleration is velocity over time. And velocity, if we pay attention to the English system, is meters per second, meters over second.
Metric system.
Yeah, thank you. While time equals seconds. Now, if you were trying to find out why this is second squared, it's easy to look at this and realize this is actually over 1.
Mm-hmm.
So you then take that reciprocal and realize this times this equals meters over second.
Very good, very good. Okay.
Now, I too thought this was interesting because, as the group before us mentioned, air pressure had a lot to do with not necessarily gravity, because gravity was affecting the objects anyway, but air pressure really had to do with the time in which both objects of different masses and different sizes landed. So that's when I researched something else which was called terminal velocity. And that's when something drops but air gets under it, preventing it from dropping at this, not exactly the same acceleration, but visually it drops different. For example, the feather that wasn't in the vacuum kind of floated down instead of coming down. And now I'll pass it to Erica Davis, who will show this by using a comb or a brush and the top of a fragrance bottle, which are clearly two different masses.
Okay, I'm Prof Davis, and I'm about to demonstrate this brush and this plastic top, which have the same, I'm going to drop it at the same height, and they're supposed to drop at two different masses.
Two different rates.
Okay. That's those the cap hit first.
I'll drop it again.
Yeah. They did hit at the same time.
Yeah, you could do it again, maybe raise it higher.
Raise it higher,
Yeah.
exactly.
Higher, yeah.
Higher, yeah.
Yeah,
You see the difference. Higher.
yeah, that was good.
Now that particular example is kind of interesting because it depends on which way she drops the cap. If she drops it upside down, the air gets under the cap, which makes it drop slower. And if she drops it the opposite way, the air can't get under it. So that's an example of how, you can drop things in two different ways so that air pressure could either get under it, which would give terminal velocity, or it could not be under it, which would alleviate air pressure, making it fall at the same rate. And now, I think to Maya, who would like to show her PowerPoint.
We have just explained the effects of gravity as well as mass and velocity and acceleration in terms of falling objects. And my presentation will summarize what we just spoke about. First, I will explain what gravity is. Gravity is a magnetic force that keeps physical objects and bodies grounded during the Earth's rotation. And the gravitational pull of the Earth is circumnavigation to the planet as a whole poles, and is equal, is weaker at the equator, and the strength also varies on the top of the Earth. And this affects how objects are grounded on Earth. And as we spoken about earlier, this is air pressure and gravity. And based on this picture, as you can see, the air resistance is pushing down. The air resistance is pushing up on object, and gravity is pushing down on object, and that affects its acceleration. Next, and finally, we'll speak about free falling objects. Gravity has many formulas that calculate for acceleration, velocity, and mass. And here are some of the examples that I have found. And as you can see in this equation, negative 980 centimeters divided by s squared, where the negative sign is indicative of the downward direction. If the object does drop down, is only vertical, it can never be horizontally dropped. And for the second equation is A equals V, which is velocity, over D squared, which is the distance squared. With velocity here, the first equation is the starting point of the object, because there is no motion, it hasn't dropped yet. So that would be V equals 0 over meters per second. And the second equation, V equals D over T. The D is the distance over time, and that explains the velocity of the object that's being dropped. The third equation is V equals the square root of G of 2 GH. that means is the equation requires constant acceleration to be true. And v is the velocity, g is the gravitational acceleration, and h is the height that is falling. And finally, we have mass. And mass is F equals ma. And this particular equation is Newton's second law of motion. And it states that the force of an object is equal to its mass and acceleration. And that determines the weight of the object and how fast it falls to the